Hello, we are Group 1. My name is Aning Tinin, and with me are Kevin Cooling, Shambi Badri, and Mark Anthony. This video, we will be representing our AI project titled Accelerating Vision High Performance Image Classification on a Data Diet. So, we are doing a comparative study of transfer learning strategy with ResNet 18. Next. The deep learning data dilemma. State of the art of deep convolutional neural network demands massive label dataset. However, many real-world applications are inherently data scarce. The main problem divided into three, which is overfitting risk. Training deep models from scratch on small datasets lead to poor generalization. Second, computational cost. Training a model like ResNet 18 from random initializations consume significant times and valuable GPU resources. And third, implementation complexity. Fine-tuning require careful handling of hyperparameters like learning rates to avoid catastrophic forgetting of pre-trained knowledge. So, the solution, leveraging pre-existing knowledge. Instead of starting from scratch, we can adapt models pre-trained on vast general datasets like ImageNet for new specific tasks. How it works? A powerful pre-trained convolutional neurons act as a feature structure. For example, ResNet 18. Its convolutional layer have already learned to identify generic visual features like edges, texture, and shape for millions of images. We only need to train the final classification layers on our smaller specific datasets. So our key benefit, performance, achieve higher accuracy and better generalization on small dataset, efficiency, dramatically reduce training time and computational costs. So next slide, establishing the proving ground. So dataset, we are using Kagos, Cat and Dogs dataset, a standard for binary image classification. So we split a rigorous by 80 and 20 split for training validation with a separate test for unbiased evaluation. Standardization, all images resize to 224 times 224 pixels. Normalization, pixel values, rescale to a 0 to 1 range. Mutation, random horizontal flips apply to prevent overfitting and improve generalization. So this is our data distributions. Technical environment, we are using framework PyTorch and hardware Google collab with NVIDIA A100 GPU. So next.
Okay, for the baseline, which is for 0.18, the strategy is a fixed feature selector. It's utilize the Resonate 18 model featured on ImageNet, and then all convolutional layers are frozen, meaning their weights are not updated in training. This leverages powerful general visual features such as edges and textures learned from ImageNet. Only the final fully connected classification layers is replaced and trained on the cast visitors dataset, and is trained for 3 epochs for establish a performance baseline with limited computation. Okay, next slide. And then the second one is the fine-tune Resonate 18. The strategy is an adaptive specialist. It's also initialized with repeated emission weights. However, in this configuration, the upper convolutional layers are unfrozen and allowed to update their weights during training. This allows the model to adapt its higher feature representations to the specific nuances of the cast versus dataset. The final classification layer is also replaced and trained. It's trained for 10 epoch to allow for more extensive learning and convergence. Okay, next. So this is the accuracy. Both models achieve high accuracy but follow different path. For the baseline, which is frozen, it exhibits a steady, consistent climb in accuracy. This stable learning process reflects the reliability of its pre-trained features. It learns slowly but generalizes well from the start. And for the second one, which is the fine-tune, it shows more fluctuation. This variability is characteristic of fine-tuning as the unfrozen layers adjust their weights. Despite the instability, it reaches a slightly higher peak accuracy, indicating better adaptation to the dataset.
Okay, this is the children learn faster. The baseline show the greater stability. On the left, the baseline frozen. Both training and validation loss decrease at a steady, predictable rate. The smooth parallel curve indicates consistent learning with a low risk of overheating. On the right, the modification model, which is fine-tuned, uh, which is show that the loss drop much more rapidly in the initial epoch, which demonstrate the faster conversion, while small jump in the validation loss occur due to the fine-tuning process. The overall downward trend confirm efficient learning. Okay, this is our conclusion matrix. The analyzing of misqualification pattern. A fine-tune provide a distinct advantage in class discrimination, particularly for one class. On the baseline, take a look at the CAT section. Here we have 990 cats is correct and have miscalculation with 21 miscalculation for dog. On the modification, we have 973 cat is correct and 38 is miscalculation as a dog. Okay, on the dog section, we have 24 miscalculation as a cat and 988 is correct detect for a dog. And on the fine-tune model, we have 7, which is much less than baseline. 7 miscalculation for the cat and have 1,005 correct pattern for the dog. Crucial finding: the fine-tune model dramatically reduced the miscalculation of dog from 24 error to 7. This demonstrates superior adaptation to the features of the dog class, given the cause of slight increase in the dog in the class in cat miscalculation. This is a performance at a glance, head-to-head comparison between the two models. Okay, here on the final test accuracy, both have 97.78%. On the dog classification, modification has better learning, which is have 1,005 correct and 7 incorrect of miscalculation with the accuracy of 99.3 plus accuracy. On the cat classification, baseline is better, which is 990 correct detect and 21 is incorrect miscalculation as a dog with accuracy of 97.9% of class accuracy. On training stability, very high and smooth predictable conversion on the baseline. On the modification, moderate and faster learning with some volatility. The training duration on baseline is 3 epoch and the training modification of modification is 10 epoch. While both models achieve nearly identical overall accuracy, the fine-tuned model shows superior performance in identifying dog, highlighting the tangible benefit of adapting the model to the target domain. Next.
Okay, the verdict. The best model depends on the mission. So here we can conclude that no single winner. The optimal choice is strategic trade-off between stability, speed, and specialized performance. Like if you choose frozen baseline and then you could get speed and efficiency, deliver excellent result with minimal training time, stability and reliability, a predictable plug-and-play solution with low risk. Use case ideal for rapid prototyping or when computational resources are highly constrained. But if you choose a fine-tuned challenger, you will get a peak performance, squeezing out the maximum possibility accuracy and adapting to domain-specific features. Downshift discrimination when minimizing a specific type of error, like false negative for dog is critical. And then the use case is best for production model where achieving the highest performance ceiling just justify the addition, training, and tuning. So next is key learning and implication. First, transfer learning is exceptionally effective. Pre-trained model provide a powerful foundation for tasks with limited data, overcoming the primary challenge of data scarcity. Number two is even a simple features extractor is highly robust. A frozen ResNet 18 backbone without any fine-tuning can achieve state-of-the-art result, demonstrating the powerful generalized of features learned on ImageNet. The third is strategic fine-tune unlocks superior performance, allowing upper layer to enable the model to learn dataset specific features, improving discrimination and pushing performance beyond the baseline, as seen with the improved classification doc. And next is for the features direction, pushing the boundaries further. So we have three, which is advanced data augmentation, introduce more aggressively technique like rotation, color jitter, and shear to further expand the dataset and reduce overfitting. Second is systematic hyperparameter optimization. Employ automate method like research to find the optimal configuration for learning rate, batch size, and dropout rate. The third one is deeper fine-tuning strategies. We experiment with selective unfreezing deeper layer of the ResNet backbone to adapt more fundamental features representation to the specific characteristic of the cat and dog domain. So that's all from us. Thank you.